Hello, welcome to my presentation. Thanks a lot for your interest. And well, first I wanted to say hi to all the reservoir computing friends. I'm just sorry that we cannot meet in person, and I just hope that the situation will change quickly and we will be able to have our meetings again in person and to see all of you. I also wanted to thank Boumediene because I think that well, the perseverance that he's having in organizing this meeting and all these sessions, I know that's a lot of work, but I think at the same time that what he's doing for the community is extremely important. So let me go to the talk. Well, as you see in this page, this is a collaboration that started already like 2 years ago or even longer when Ludmila organized a meeting in Constance. There was a reservoir computing and dynamical systems meeting, and then well, Joseph Teichmann he came to this meeting and he realized of various connections between what we do in reservoir computing and some techniques that appear in rough path theory, which is, if you want, part of a stochastic analysis. So the collaboration is with Christa Cugiero from the University of Vienna, Lucas Gonon, who was my postdoc in St. Gallen, and now he's a professor at the LMU in Munich, Ludmila Grigorieva in the University of Constance, and Joseph Teichmann in ETH. So the point is the following. Again, this is a reservoir computing talk, and the goal here is to use certain geometric techniques, let's call it like that, to explain the success that we have in the use of randomness in reservoir computing. I mean, this phenomenon that inspires all of the fact that we are just randomly generating these dynamical systems, and then, well, we just train a linear regression and all of a sudden it works. Why is that so? So, as I will emphasize later on, there are several ways to tackle this problem. One would be more traditional, in the sense that, well, you just use a stochastic analysis to prove that that is so, and you formulate pack bounds and things like that. We have papers in that direction. But another way to go about it is through the combined use of two ideas. The first one is this strong universality that I will introduce, and the second one is random projections. So the combination of these two ideas gives what, in my opinion, is a very beautiful explanation of the reservoir computing phenomenon, at least in the polynomial setup. And this is what I want to show you today. What you will hear today in this talk is, if you want, a discrete time version of what Joseph Teichmann will be showing you in his live talk, and probably he will be recording one too in the continuous time setup. Yeah, I will refer to this talk several times, and it is something that if you like the topic, I strongly encourage you to listen to that one too. Anyway, so let me start with something that most of you know, which is these extreme learning machines, right? So extreme learning machines, this is just randomly generated neural networks, in which all you do in order to train is to solve a linear regression problem in the last layer, and that's all the training that you do in order to come up with a neural network that approximates a given function, right? And so this is a recently old idea, so it goes back to this paper by Wang Bing Huang in NTU in Singapore in 2006, and well, like many advances in dynamics, it's coming from basically engineers. So this gentleman, he's an electrical engineer, and well, they are not so much interested in the theoretical aspects that go with this phenomenon. They go for applications, and actually I'm telling you, it's engineers who do wonderful applications with this relatively simple idea. So I encourage you to Google up the page of this gentleman Arindam Basu, also in NTU, and well, these people, they are not interested in high quality training like what you see in many deep learning tasks. All they need is to be able to handle in real time via online training huge volumes of data coming from sensors, wearable devices, and all types of Internet of Things type of devices. So the idea is already pretty old. And of course, this is just a static paradigm. We need to go to something dynamic, like what we do in reservoir computing. So if we want the reservoir computing, the definition that I'm going to give you of reservoir computing is just well, the recurrent neural network version of this. So as you well know, well, we just have an input-output system that can be realized in the form of a state space system where the state equation is being randomly generated. So and then the other constraint that we impose is that the readout is linear, so that as I write in here, data-intensive applications become tractable. And then, well, this you have to take with a pinch of salt, but it's also important. Inference and theoretical performance evaluation becomes possible, because ultimately, even though we are going through a nonlinear system, ultimately the estimation problem is linear, right? So, but in any case, this would require some more details in order to make it precise, what I just said. So, okay, this is the picture that we always show, but as I told you before, what this means is that we have a state equation. So then the notation here will always be the same. So the C's are going to be the inputs, the Y's are going to be the outputs, and then since we are using a state space representation, the X will be the states, right? So the states, they live in a vector space or a manifold which is typically of much higher dimension than the dimension of the input C's and the output Y's, right? And then again, we talk about reservoir computing when this F is randomly generated, or at least mostly randomly generated, and DH is, yeah, if possible, linear. It has to be first static, and second as simple as possible, and in most situations, if we want to make things big data compatible, it better be linear. So there is a point that probably is not sufficiently emphasized, but is very much present in the first papers about this subject, that as it has been said already in other talks, was introduced by Herbert Jäger in his science paper, where he does these wonderful applications to forecasting and equalization, and also by Maas in other collection of papers where they talk about basically the same phenomenon, in the case of Maas under the denomination liquid state machines. And Maas himself, he does emphasize this multitasking business here. So multitasking is the possibility of actually processing the information. So actually you have to think of the state equation as the nonlinear device hidden in this capital F that is processing the information, and then in order to do something with that information, or let me say it better, in order to do several things simultaneously with that processed information, you train separately different readout layers. So let me give you an example. Suppose that the C is say a time series of prices or returns in the stock market, and then out of that you want different Y's to be, for example, instantaneous volatility, filter instantaneous volatility coming with those C's, or forecasted volatility for next day, next week, or next month, or forecasted trends in the next week of those returns, yeah, these are different things that you can ask about the same input. So actually you just run this multitasking would be just running the z's through this state equation and then training different h's for all these different tasks that you want to solve. That is extremely important in many situations. Well, if you are doing things on the computer algorithmically, this is obviously of much importance because you need to run your input only once through the F. And then for our friends who are doing hardware realizations, they will tell you that what is, for example, energetically expensive is this part of the procedure. So non-linearities in hardware, they are usually expensive, and then the readout is much more affordable. And so the fact that you can solve many tasks just by processing the information only once is extremely important. I'm not saying that this is feasible, right? So this is something that we want, but I'm not saying that this can be done. And the reason why I'm bringing it up in such detail is because the feature, the mathematical feature that makes this possible is this strong universality that I will be discussing later on. So is the possibility of, with a given approximate state equation, to approximate many input-output systems just by changing the W. So actually this multitasking, the ability of having multitasking or the possibility of having multitasking will be the definition of this strong universality. Very good. So here there is something that I need to say, because you see we are calling reservoir computing to state space systems, and this is probably one of the most venerable fields that you have when it comes to control theory, systems theory, and so these go back to 70 years of literature with huge names represented that I wrote down in here. And so you see what I just told you. I mean, I give you an input-output system that I want to model, that I want to learn, because we are going to ultimately train this system via supervised learning at the time of solving this linear regression. So the fact that we are realizing a given input-output system as a state space system, this is a classical problem in systems theory. That's the realization problem, right? So this has strong links also with filtering theory, right? Because there are some situations in which models of the type that I just wrote down for you, well, those X actually encode unobservable factors that we want to filter out of the observation equation. So think of all these stochastic volatility models where the X is actually the volatility or the variance, right? The conditional variance. So then there are also links with a much more recent theory, which is the theory of non-autonomous dynamical systems. As I say, this is very recent, and then there are these recent works by Gandhi Manjunath, Peter Tino, and Ortega that I like very much. And well, those links, I think that they need to be fully exploited, first for the beauty of the maths that go with it, and also because they truly say something about applications. And then I wanted to bring up something, because you see there are these links, right? But at the same time, as you will see later on in the presentation, we are always working in a setup that has to do with semi-infinite inputs. So you see, when you are doing, for example, control theory, and you're solving the reachability problem or the observability problem, you always work with time-dependent flows, in the sense that in a control problem I give you a point, and then the controllability is how do you have to choose the control so that you go from point A to point B. In our situation, since in many cases we will be dealing with stochastic inputs in a stationary regime, or we will be working in a fading memory situation that is not a finite memory situation, we are obliged to work with this semi-infinite inputs framework, right? So so what I'm trying to say is that all these results in control theory and so on, they do not automatically apply to our setup, right? And then at the same time, the goal that we are solving is typically different. So here is learnability our problem, while in all these theories is different, right? So in control theory is obviously controllability and so on. Just pick up any book on the subject and you will see that there are many mathematical facts that we can take advantage of, but it is not the same. So having said that, I wanted to mention that you see in the reservoir computing setup we have proved various universality theorems, and they help, or they bring you light to, for example, this realization problem that I told you about, right? So a corollary of these universality theorems that tell you that, well, there are all these families, equal-state networks, state-affine systems, we will talk about them later, that are universal approximants in the fading memory setup. Well, all those people, they are state space systems. So ultimately, we are not solving the realization problem in the sense that we are not proving that a given input-output system in the fading memory time invariant causal framework can be realized as a state space system, but we are actually also proving, what we are actually proving is that, well, you may not be able to realize, but you at least will be able to approximate as well as you want with one of those state space systems. Okay, so there is this yeah, as European bureaucrats like to say, cross-fertilization between all these fields and all these ideas, and is very interesting, I would say. Right, so let me conclude this introductory part with a recap. So our definition, I know that this is much of a reduction, but this is the idea that you need to keep in mind. So for us, reservoir computing will be the possibility of approximating an input-output system that I am observing. So I don't know the oracle, so we are in an agnostic setup like we always do in machine learning in general and supervised machine learning in particular. And so is the possibility of modeling or approximating that object with a quasi-randomly chosen state space system with sparse features, if possible, right? And then we want that the readout is linear, okay? So an example are the equal-state networks that you already saw in other presentations. So here, usually, well, the thing that is not random is the fact that I choose this functional prescription, right? But the A, the C, and the zetas, they are randomly chosen. And if you look at the papers by Herbert Jäger, for example, this A and this Z, they are going to be typically sparse, and then all you tune is this W. So it's sparsity, randomness, linear readout. This is the if you will, the holy trinity of reservoir computing, and something that I will not discuss here, but there is a huge community out there very much interested in this, is the fact that is the possibility or the availability of realizations with dedicated hardware. Okay, so I have papers with colleagues in these fields having to do with time delay reservoirs. That there are beautiful problems that you can mathematically tackle in that framework. But here I will focus just in what I told you. Okay, now I get into the core of what I want to do, right? So let me go back to this one. So what I want to explain to you using these geometric arguments that I discussed with you before is the possibility of doing exactly this, right? And moreover, I want something more. So apart from these random choices and linear readouts, I want that the state equation, which in the case of the ESN is this part, actually is good for any input-output system that I want to approximate. So you see, you are modeling an input-output system, and then, well, any universality theorem of those that you can find already in the literature, they will tell you that there is an A, a Z, and a zeta such that they approximate that given to you input-output system. You have to find the A, the C, and the zeta, and the W, right? However, what I want is to find that is what I call weak universality. A strong universality would be to find an object like this such that for any u that you give me, in order to get that approximation, all you need to change is the W, but the A, the C, and the zeta, they are the same. So that would be a strongly universal equistate network, right? I give you the A, the C, and the zeta. You change the input-output system that you want to approximate. All you need to do is to retrain the W. So I don't want to start all over each time that I give you a new input-output data generating process, so that because well, finding this, as all of you who have done applications know how tricky finding those is, all I want to have to do is to retrain the W. Okay, so that's the definition of a strong universality. So this is much stronger. First observation, this is much stronger than the weak universality that we are used to. An example of which could be in the framework of neural networks, all these Seebenko-Hornig theorems. And for ESNs, well, I will show you in a second things that we proved in the recent past. Okay, so second observation, notice that if you have this strong universality, then all of a sudden this multitasking that I was telling you about becomes automatically a possibility. Because you see, if I tell you that you don't need to change the A, the C, and the zeta when I change the input-output system, and all you need to do is to retrain the W, that is multitasking, okay? So again, one thing is to be able to, one thing is to want this, and the other thing is that is this true, right? So so here comes this observation from Joseph Teichmann when we met in Ludmila's talk a few years ago, in which he immediately realized that there are situations in which this actually happens. This is what truly is going on, and the framework in which he took the inspiration from is this field of control stochastic differential equations. So a control stochastic differential equation, just if you want a differential equation, you have these inputs that are usually, well, they could be semi-martingales, they could be rough paths, they could be, it's just inputs, right? And then this control stochastic differential equation, well, the input is going to be this input noise, and the output is going to be the solution, right? So the factor that takes you from this input to this output can be factored out as the composition of two objects. So the first one is what they call the signature process, which is well, just listen to Joseph's talk, but it's a relatively sophisticated object that you define in an admittedly infinite dimensional space. So actually it's a Hopf algebra with as many generators as the dimension of your input. So this is an infinite dimensional object. And then, well, you solve that thing, right? And then a linear readout of the solution of this a linear readout of this process is actually giving you well, the input-output relation between the input noise and the solution of the control SD. Okay, so this already happens, right, in some situations which are actually very close to what we are doing. So so here is where the inspiration came from, and that's why what you are going to see, the construction that I'm going to show to you, is we will call it 6ASSAS. So it's going to be the signature, state-affine system, because well, the state equation that defines well, the solutions that I will show are strongly universal, are very close to basically Euler discretizations of this signature process that Joseph was talking about. So just to emphasize the idea, here you have an example of weak universality statement. So I give you an input-output system, and then I tell you that there exists an A, a Z, and a zeta. Eventually, there are improvements of this theorem that tell you that you can choose them randomly, such that you can approximate the given filter, right? But you change only the U, and you will have to change the A, the Z, and the zeta, right? So again, the strong universality I'm running after is the one in which I will be able to respect the other building blocks of this network architecture, and then I will only change, I will modify exclusively the W. Okay? So let's take our first step towards strong universality. And the building block that I will use for this strongly universal construction are these Volterra series. So this is again extremely classical. So if you want, there are two pieces of work that need to be quoted here. So the first one is, you see in the dynamic fading memory setup, Volterra series, well, I forgot to say, with uniformly bounded inputs. So these Volterra series were the first universal object that was spelled out in the literature. There is this beautiful Boyd and Chua paper in 1995 where they prove exactly what I just told you, that in the time invariant causal fading memory setup with uniformly bounded inputs, Volterra series are universal. It's a relatively easy consequence of well, a compactness result that they have together with the Stone-Weierstrass. It's not that complicated. And then there are all these papers by Sandberg, again the engineers, who proved all sorts of results and mathematical facts in connection with this series. In particular, truncation bounds, which is something that I am very interested in, and which is the second long expression that you have down here, right? So the only thing that Ludmila and I added to that literature is the fact that instead of considering forward-looking or flow-like input-output systems like Sandberg does, we went to the fading memory setup, right? And so that is again with semi-infinite inputs, and well, that allowed us to formulate bounds that involve not only the Taylor part of the bound. There is one extra term that comes from these fading memory characters, so we're able to prove the existence of a sequence that goes to zero when you go towards minus infinity. In any case, this is the result. But for those of you who never saw this Volterra business, so Volterra is just the Taylor series expansion of a filter, right? So I give you a filter. Here, this is a map between two Banach spaces. You can take Frechet differentials, and then you can do Taylor series expansions. So if your filter is analytic, well, you can conclude that it admits an expansion like this, where these coefficients that you have in here are just the partial derivatives of the filter, right? It's as simple as that. And then when you truncate, if you are in the Sandberg situation, you would get basically the Taylor remainder, right? And since we are in the fading memory situation, we need to add this extra term, right? So this is just a sequence that goes to zero when the truncation in the L goes to infinity, because there are two types of summands here. So there are these M summands, right, that go with these M's that you see here that tell you what are the terms. So actually what you are doing is you are expanding this filter as a series in which you have all these polynomial terms, right? In which these monomials are powers of the inputs, right? Evaluated at points in time at different points in the past, right? The higher the m is, or the lower it is, the more in the past you go. So, and then the j tells you how many of those people you have. So that tells you basically the degree of the polynomial approximation that you are using in this Taylor expansion. So now I go back to this strong universality idea. Here you have a situation where you have some sort of a strong universality, because look at the truncated expansion. Well, if instead of expanding this u, I take another filter, call it capital V, then well, the basis that I'm using for expansion would be always this polynomial basis. The only thing that would change is this g, right? So these are the coefficients that I would need to change if I want to model a different guy. However, the basis of this expansion is the same. This is extremely classical. Actually, it goes back to Weierstrass's approximation of continuous functions by polynomials. But this is ultimately what we are doing. And here you have this universality, in the sense that this is a strong universality, in the sense that these c's, they do not depend on the v, right? They do not depend on the u. The u dependence, you find it only on these g's that are linearly multiplying these monomials, and very important, you also find it in the rate of approximation. So it could be that, well, you change the coefficients because you are changing the u on me, and then, well, you will get an approximation, but the approximation will be better or worse depending on the object that you are actually approximating. But this is just a suggestion, right? Or something to inspire you towards this strong universality, because you see, there is no state space representation. This is just an input-output system. So what we are going to do now, we are going to create an input-output system whose solution is going to be this strongly universal basis, right? This is what we are going to do now. So here you have what I just said, right? So that you have it in writing, in case you want to look at it in detail by stopping the video. So this is what we are going to do, is we are going to find a state space system whose solutions will be these terms, right? And then the solution to this question will be this signature state affine system. Signature because it resembles very much this this signature process that you find in the factorization of the solutions of controlled stochastic differential equations with a linear readout. And then a state affine system because it will belong to this family of non-homogeneous state affine systems that Grigorio and I prove are universal in the fading memory setup a couple of years ago, right? So they do belong to this this family. So I remind you, the state affine systems, these are equations, state equations, in which well, what you have is that the state at time t depends on the state at time -1 via a polynomial equation in which is basically a polynomial on the inputs, but this polynomial has matrix coefficients. Okay, so we will see an example in a second. Okay, so now you have to bear with me for 5 minutes because we are going to explain this construction. So the way this goes is, first, we are always working in this uniformly bounded inputs situation. So these are semi-infinite sequences, but for each term they live on a compact, on a closed and bounded interval. Okay. And then the state space of this 6-ASSAS system will be these tensors, right? So I have to fix an L, which actually will have to do with well, the truncation of how many steps into the past I look at. This will be tensors of order L in Rd. So the reason why I'm doing it with tensors of a given order is because I want to stay finite dimensional, basically because I want to formulate approximation bounds, right? However, if you want to make a better link between this and the constructions that Joseph Teichmann will be showing you in his talk, the right way to make that link would be not to impose bounds on this L. So you would take tensors of any order. You would take the actual tensor algebra on RD, right? So this is an faithful representation of this Hopf algebra, that infinite dimensional, that he will be showing you in his talk. Okay. And then finally there is this order lowering map, which takes you from tensors of order L plus 1 to tensors of order L, basically by fixing the first component in the tensor. Okay, so you start with something of order L plus 1. You see there are L plus 1 elements here, and here you have one less, right? Okay, so how do we use all these ingredients? It's via one more final construction, which is these van der Monde vectors. So you see the CT, we fix again P and L, so L will be how many time steps I look into the past, and P is going to be the order of the polynomial approximation, truncated polynomial approximation that I will be looking at. Think of this Volterra expansion that you saw before. And so out of that we construct this P plus 1 tuple made out of powers of this CT, right? So here the inputs are one dimensional, right? So there is this CT, which is a number, and then you take the 0 up to P powers of it, and this gives me a P plus 1 tuple, right? Well, I do it for T, I do it for T minus 1, I do it up to T minus L, and then I take the tensor product of that, right? So this gives me indeed a tensor in this space, okay? A tensor whose components, if you look at the canonical basis, right, are all the monomials on this CT minus 1 up to CT minus L, and that contain powers up to order P in each of those variables, right? So if you are thinking of a polynomial expansion of a filter using those monomials as a basis, this is the gentleman that you would like to have, right? Because it contains all those approximants, which are actually universal approximants, as you saw in this Volterra theorem that we discussed together. And so this is what I want to have as a solution, if you want. So I'm going to formulate a state space system whose solution will be morally this, okay? So that's what we achieve with this 6S filter. So the way it goes is via this state equation. So the state, so again, this leaves, the states, they live in this space. And then the way in which we do it, well, is the state at time t. Actually, in order to get it, all you need to do is first you lower its order, and then you multiply by this van der Monde vector associated to CT. And you tensor it with this, right? And then there is this non-homogeneous term that you choose in a specific way that is not important now. It was detailed in the previous slide. So for reservoir computing people, you know that this equal state property, fading memory property, these are desirable properties. So what we can prove is that if you choose the lambda in such a way, then well, this state equation satisfies the equal state property and the fading memory property. Therefore you have a unique solution, and the unique solution is well, basically this CT hat that I showed to you before. There are all these extra terms, but these extra terms, they are just repetitions with positive coefficients of the monomials that you already have in CT hat. Okay, so this 6S filter is doing what I told you before, is producing these monomials that are strongly universal approximants for input-output filters in this fading memory category. Okay, so what can we do with that? Before I tell you that, let me emphasize that this is indeed ASSAS. So for those of you who know what that is, so ASSAS, as I told you before, is something that behaves like this. So the xt depends on the xt minus 1 via this PZT. So this PZT is a polynomial on the C, but the coefficients, they are matrices that are multiplying the xt minus 1, and they are producing another tensor in the same space. So, well, this PZT, actually you can write down the previous equation like this using the basis EI, the canonical basis, and then here you have the polynomial in CT, and these are the matrix coefficients. So this is a linear map that is multiplying the I minus 1th power of CT, okay? And then the non-homogeneous term. So these are, we know that these people by theorem, because we proved it some time ago, are weakly universal. So what we are proving with this theorem is that, or with the theorem that will come in a second, is that there is actually a choice in this family that it happens to be strongly universal, which is not that surprising if you know that polynomials are also strongly universal in the category of continuous function, right? So this is the theorem that I wanted to show you, right? So if I give you a U, well, all you need to do, if you want to approximate it to a given error budget, let's call it like that, is, well, you just take your 6S system, you crank it, and then you just find me the coefficients that produce this approximation. But this approximant is the same for any U, right? There is nothing in the 6S construction that talks to the U. The only way in which the 6S function, 6S state representation talks to the U is through the quality of the approximation, right? So this sequence that gives you the error depends on the U, right? So, but in any case, this is to tell you that we achieved this strong universality that we wanted. In order to approximate the U, all I need is to run a linear regression on the output of the 6S process for a given input. Okay? So, right. So this, well, the first 3 bullet points is what I just told you. So we achieved this strong universality. There are 2 more points that I wanted to emphasize. So the first one is that, you see, this has tremendous numerical efficiency. What do I mean here? So the first one is that this is for people who know about signatures, right? So when you use signatures to learn well, the solutions of control stochastic differential equations, that construction is relatively sophisticated in the sense that it is a bunch of iterated integrals. At the same time, that construction is directly in continuous time. In applications, usually you have discrete time series, right? So the first thing that you have to do is to put this in continuous time. People use this lead-lag transformation traditionally, but you see these iterated integrals, they are costly to compute, and that's why it's rare to go beyond order 3 in those expansions. Here, that is not like that. I mean, here there are only these polynomials. It is already formulated in discrete time. And at the same time, another setup where you see the efficiency of this is the fact that you see, if you want to compute this solution, right? The solution at time t is something relatively complicated. You might have a lot of terms in this sum, right? And then at each time t, you would have to compute this convoluted expression. However, if you use the state space representation, all you have to do in order to go from time t to time t plus 1 is just to basically do this little tensor product, right? So it is very efficient, and well, and actually that's one of the well-known advantages of a state space representations, and that's why we do it. That's why we do this after all. Right. However, the dimension may be huge, because this is a tensor space. It's exponential on the order at which we are working, and then you see we set to prove that, well, we can do reservoir computing with randomly generated people. So all I gave you is somebody who is strongly universal, but there is no randomness here. I didn't choose anything randomly, and then, as I said, the dimension could be huge. If we want a representation, we need to go infinite dimensional, like you will see in Joseph's talk. How do we go about that? So, as I told you in the introduction to the talk, there are two ways to go about it. The first one would be using a standard stochastic analysis, concentration inequalities type of techniques, in order to prove that various families have these properties. So, in the sense that you randomly generated and you can have arbitrarily good approximations with high probability, and that is something that we have done for ASSAS and for ASSAS in papers with Lucas and with Ludmila. So just look at our web pages, you will find them there. The approach that we will take in this talk is different. So is this geometric approach that has to do with these random projections, right? Is this use of Johnson-Lindenstrauss. So I already tell you what we will see is that a random projection of this high-dimensional polynomial SAS representation can be randomly projected into something which is much smaller dimensional and is still a SAS system, but it will be randomly generated. So that's the idea, but let's see how we can actually realize it. So for those of you who never saw the Johnson-Lindenstrauss, so this is a relatively how to say it, this is one of the tools of choice when you are doing dimensional reduction in machine learning. And what this lemma, which should be called a theorem in my opinion, tells you is that if you take a Hilbert space, so this is truly a Hilbert space phenomenon. You truly need an inner product, because well, you are using profusely the parallelogram identity. So if I give you a Hilbert space and you choose Q points on it, and then you randomly project this space, actually the distances between these original points and the distance in the projected space between these Q points are going to be respected up to epsilon. And then there is this relation between the epsilon that you choose, how accurate you want to be in the distance, how the distance are preserved in this projected space, and the dimension of these random projections, right? So it's this formula that you see here. So the more accurate that you want to be in respecting the distances between the projected points, well, actually the higher dimensional the projection will have to be. And then there is also this, the reason why I call these random projections is because there is an improvement of the Johnson-Lindenstrauss lemma that tells you that actually you can build this F by basically randomly drawing a matrix of dimension, well, K by dimension of V, you just draw randomly this matrix with normal entries, IID, and then you can actually bound the probability that the f is going to do this job. Okay, so there are three ingredients: the epsilon, so how well you want to respect the distance between the projected points, right? The k is the dimension of the projected space, so the smaller the epsilon, the higher the k is going to be, and then the probability, if you draw randomly this projection, that this the probability that this expression is respected. Okay, and then I will not get into that because we are going to do it all with this prescription. If we succeed in doing this, actually the sparsity can also be explained, because there are papers, you have the reference at the end, that tell you that actually this f can be chosen as a sparse matrix. Okay, so let's see what the goal here is. The first, I just need a couple of theoretical tools. The first one is this Q norm. So it turns out that so you have the V is this Hilbert space. You take this Q set of points, and then you can actually define this norm in the span of those points, right? Just basically by taking this inf that you see here, and using this Q norm, that's how we call it, you can prove this identity, right? So let's look at it for a second. So what does this identity tell us? Look, if the f is not an honest-to-God projection, in the sense that it is not necessarily an orthogonal matrix, right? If this was a real projection that is self-adjoint and idempotent, then well, what we would be projecting here, this would be the projector into the orthogonal component of the target of this f. Okay, so you see, if this was a projection, then here what we would obtain is a 0, right? This would be equal to 0, right? Which is ultimately a translation of the fact that, well, in a k-dimensional space, you have at most k orthogonal vectors, right? So what this is telling us is that, well, if you are going for not orthogonality, but for epsilon orthogonality, well, actually, what you may have is not k orthogonal vectors, but exponential of k epsilon squared. All I'm doing is I'm undoing this relation here. So it will not be k orthogonal vectors, it will be e to the power k epsilon squared epsilon orthogonal vectors, right? So if you are willing to accept this epsilon here and not 0, that's what this lemma is telling you, right? So and this is the main tool that we use in the construction of bounds for this approximating projected state space systems that we build in this theorem. So this theorem is a general fact, is ultimately diagram chasing, so it's a factorial construction, and what this tells us is that suppose that I give you this family of state space systems that are defined in this high dimensional space. So this capital N is very big, think of it like that, and then these people, they are contractions on the first entry, on the state variable. And then what I do now is I construct a JL projection using a bunch of spanning points that satisfy this relation. So what this theorem tells you is that if you respect certain constraints in the rate at which this thing is contracting, and that puts into relation this lambda, this contraction constant, and the norm of the projection. So this triple bar norm is the norm operator with respect to the Euclidean norm. Okay, so what this is telling you is that if you have a state space system that satisfies the equal state property and the fading memory property, then you can actually project this gentleman to somebody who has also the same property, and but is defined in a much smaller dimensional space, right? And here is the prescription of how to do it, right? So these are just matrices and they are transposes, right? So I am taking somebody who is ESP plus FMP, and then I obtain a randomly projected object that satisfies these two conditions. And then what we are able to do, basically using the lemma that you saw in the previous slide, is to bound the error that I am going to commit. So this is the projection error. By reducing the dimension, this is the error that I am committing, right? So, two things that I wanted to emphasize, that there is an epsilon here. So the importance here is that of this expression is that I can make this error as small as I want. There will be a price to pay on the dimension, because as I told you before, there is a relation between the epsilon and the k, right? So I want a better approximation, then, well, the gain in dimension reduction will be smaller. And then there is this operator norm, which can be very big. Actually, it can be very big, but actually at least in expectation, and therefore we can use concentration inequalities. You can bound it. There is this Gordon's theorem that tells you how to put how to bound the expectation of this as a function of the square root of the number of columns and the number of rows, actually the sum of it. So these are general factors I said. So I give you somebody up, I randomly project it, I get somebody down. If up we were FMP plus ESP, downstairs we have the equal state property and the fading memory property. So we have filters up, we have projected filters down, right? So once we have the general fact, we can apply it to this signature filter, the ASSAS filter that you saw before, right? So this gentleman, he was strongly universal, but it was defined in this tensor space that was huge dimensional. But then we can randomly project it, and as we did before, I can find a bound which is linear on epsilon for the error, for the projection error, for the dimension projection, or for the dimension reduction error that I am committing. Okay. So seen like this is just a fact, right? But the importance of that result is not that corollary is this theorem, because using various central limit theorems for martingales and various results in stochastic analysis that you will be able to see in the paper, you can prove the following, in my opinion, astonishing fact, and is that you see, you take this 6-SAS system. So if you randomly project it, what you obtain is another 6-SAS in which you have, it's a 6-SAS basically because you have these polynomial terms and then these matrices, right? Matrices in a small dimension. And then this non-homogeneous term that is represented by this capital B, this is a vector, right? But these people are random matrices. Random matrices whose law I can make totally explicit. So what this is telling you is that, well, if you want to carry out this construction, actually you don't need to go all the way from the beginning to formulating the 6-SAS state equation to compute it, to randomly project it. No, you can start automatically downstairs in the reduced space just by generating these random matrices, right? And moreover, I am able to tell you what is the quality of the approximation that I will be obtaining and what it represents. So suppose that you have a 6-SAS system of this type that I generate by computing a few random matrices using this law. and then I do it in dimension 50, right? So we have a 6S system in dimension 50. What this, and then if you just do Mackie glass forecasting like Herbert Jäger does in his paper, you will see that it works very well, right? Not with 50, it will have to be with something higher. But in any case, we can explain why that performance is good, because we know by theorem that this 50-dimensional representation, actually it has to do with an e to the power 50 Taylor series expansion of the data generating process that we are trying to model and that we are trying to use to forecast. So that's why these randomly generated objects, they work so well, because even though they are randomly generated people, up to an epsilon error, they correspond to high order Taylor series expansions before you carry out these random projections. So if you want, this is the punchline of this talk, right? Is we have these randomly generated objects. Why are they working so well? Well, because up to epsilon, they are representing something that upstairs corresponds to extremely precise and huge dimensional approximations, right? So of course they work well. So this is what I wanted to tell you. There are many things that I put under the rack and details and so on. Many of them you have them in the paper. Well, all of them you have them in the paper. But there is one final consideration that I wanted to make, which is the bounds that you saw in here. So there are all these error bounds and so on. So if you just work them out and you look at examples and these bounds, they are not great, right? Well, if you are interested in explaining the reservoir computing phenomenon and you want to see why this randomness is appearing and so on, it's fine, then you don't care about the quality of those constants. But if you're interested in efficiency, and we are all interested in that, you want to have good constants. And those constants, as I said, are not good. The reason why that is because you see, the way in which we are applying this Johnson-Lindenstrauss theorem is really suboptimal, in the sense that ultimately, if you look at well, before we do reduction, right, we go to this theorem. What we are doing when we are approximating a U via the solution of the 6S process, we are basically estimating this W. This W estimated on the solution of this, which is just basically polynomial. So ultimately, actually it's monomial. So we are running, in order to carry out this approximation task, a polynomial regression. Everybody knows that polynomial regressions are not good because they are poorly conditioned. There is a lot of redundancy in the information carried out by that these monomials are carrying, right? So before you set to solve a polynomial regression, you have to do a previous reduction. Usually what people do is PCA, and that would give us one more term in this approximation bound, but that would allow us to severely reduce the dimensionality before we apply Johnson-Lindenstrauss. If we do that, we would drastically reduce this M and this N that you see here. And that's what makes these bounds mediocre, okay? So that's something that we are actively looking at, and I hope that this will be the subject of another talk in not so distant future. But in the meantime, this is what we can show to you. So I emphasize again, for those of you who like this topic and who enjoy this talk, I encourage you to listen to Joseph's talk, because it will have a different flavor. It will be mathematically more sophisticated, but it's beautiful mathematics. So anyway, this is what I wanted to tell you. Let me flash at you the references that I talked about. So here you have them. So this is it. Thank you very much for your attention, and then I will see you in the live talk. I think we have it on the 22nd, I will be, well, there, Boumediene, he asked me to make a general introduction about reservoir computing, so it will be a general, all public talk. It will not have anything to do with this. But anyway, I will be very happy to see you there. Thank you very much for your attention and for your interest, and see you later. Bye.